Dark openings, one of the most baffling and peculiar phenomena in the universe, remain a subject of extraordinary review and interest among space experts and physicists alike. These heavenly elements, described by their monstrous gravitational draw and the total non-appearance of light outflow, represent a limit beyond which the known laws of physical science stop applying. First speculated by Albert Einstein in 1916 as a result of his theory of general relativity, dark openings were simply theorized until mechanical advancements allowed their indirect identification during the 20th century. The turning point came during the 1960s when space experts studying the Cygnus group of stars accidentally discovered an unusual celestial object, a brilliant blue star producing high-energy X-rays. This star, orbiting an invisible companion, challenged regular explanations until it was revealed to be caught in a gravitational embrace with a massive dark opening, Cygnus X1. The discovery of X1 provided clear proof for the existence of dark openings and began a new era of investigation into these infinite conundrums. Cygnus X1, found around 6,000 light-years from Earth, boasts staggering properties. It is incredibly dense and applies a gravitational force so intense that not even light can escape its grasp. This defining feature earned it the moniker dark opening, embodying the essence of these mysterious objects. Some subsequent exploration efforts have uncovered a variety of dark openings scattered throughout the universe. Estimates suggest that the Milky Way galaxy alone may harbor more than 100 million dark openings. Despite their elusive nature, which makes precise detection challenging, space experts have identified several candidates within our galaxy, ranging from stellar mass dark openings formed from the remnants of massive stars to supermassive dark openings residing at the centers of galaxies. The gravitational impact of dark openings extends far beyond their immediate vicinity, shaping the elements of cosmic development and influencing the fate of surrounding matter. Objects that venture too close to a dark opening face a destiny fixed by its relentless force. They are drawn unyieldingly toward the event horizon, the final turning point, where they are subjected to extreme tidal forces and ultimately consumed by the singularity at the dark opening's core. This catastrophic interaction, known as spaghettification, represents the extreme manifestation of a dark opening's gravitational strength. As an object approaches the event horizon, the gravitational gradient across its length becomes so extreme that it is stretched and contorted into a filamentary structure resembling strands of spaghetti. The forces applied by the dark opening overpower the internal bonds keeping the object intact, resulting in its disintegration into a stream of matter destined to merge with the singularity. Despite the allure of dark openings as invaluable laboratories for testing the limits of physical theory, they remain shrouded in mystery and intrigue. The mission to unravel their secrets continues unabated, driven by a desire to understand the fundamental nature of space-time and gravity itself. In the vastness of the universe, dark openings stand as silent sentinels, beckoning humanity to explore the depths of the unknown and expand the boundaries of human comprehension. Despite the tremendous distance separating us from the nearest dark opening, roughly 1,500 light-years away, questions and concerns about their potential impact persist. In 2021, researchers achieved a monumental breakthrough by capturing the first clear image of a dark opening, specifically M87, located at the center of the M87 galaxy. This remarkable achievement provided crucial insights into the nature of dark openings and their elusive structure. The visual data revealed that dark openings have intricate layers, challenging the traditional perception of them as solitary entities of pure nothingness. Through meticulous analysis and image stitching, scientists identified 3 distinct layers within a dark opening. At the outermost layer lies the event horizon, a critical boundary marking the point of no return. Once an object crosses this threshold, gravitational forces become insurmountable, ensuring its inevitable plunge into the dark opening's depths. Moving inward, the photon sphere constitutes the second layer, where light orbits the dark opening in perpetual bondage. Any photons that dare to venture into this realm succumb to the overwhelming gravitational pull, trapped forever within the cosmic embrace of the dark opening. At the heart of the dark opening lies the singularity, the third and final layer, where the laws of physics reach their ultimate limits. Here, matter undergoes unfathomable compression, collapsing into a point of infinite density. It is within this enigmatic singularity that the familiar laws governing the universe cease to apply, plunging researchers into a realm of profound uncertainty and theoretical speculation. The complexity of dark openings and their inherent variability presents significant challenges to our understanding. While they adhere to a common three-layer structure, each dark opening exhibits unique characteristics and behaviors, defying simple categorization. As such, traditional methods of scientific inquiry prove insufficient for studying these cosmic behemoths, necessitating innovative approaches to unravel their mysteries. Indirect observation remains the primary means of studying dark openings, as direct investigation is rendered unfeasible by the immense barriers posed by their gravitational forces. Attempts to launch probes into dark openings would inevitably result in their destruction, crushed into obscurity by the relentless forces at play. Nevertheless, researchers persist in their quest to decipher the secrets of these cosmic giants. Various theories, ranging from stellar collapse to cosmic dynamics, offer tantalizing glimpses into their origins and behavior. Notably, NASA's study of the cosmic center of M87 revealed compelling evidence of a supermassive dark opening exerting its gravitational influence over vast cosmic scales. Despite these mysteries, the pursuit of knowledge continues unabated, driven by humanity's inherent curiosity and thirst for understanding. While the enigma of dark openings may elude simple comprehension, the steadfast dedication of scientific inquiry promises to illuminate the darkest corners of the universe, unraveling the profound secrets hidden within. Roy Kerr's groundbreaking work in 1963 presented a paradigm-shifting perspective on dark openings, proposing a revolutionary theory of rotating black holes that defied conventional understandings. Central to Kerr's model was the concept of the aerosphere, a region surrounding the dark opening where divergent forces balance gravitational collapse, preventing matter from collapsing further inward. This novel domain displayed curious deviations from traditional physics, hinting at the profound mysteries concealed within dark openings. However, the most intriguing implication of Kerr's theory was the prediction of an Einstein-Rosen bridge, informally known as a wormhole. This hypothetical structure represents a potential gateway through spacetime, offering a conduit between distant regions of the universe or even parallel universes. The idea of wormholes stems from the intricate interplay between reality, as described by Einstein's theory of general relativity. In this framework, existence is woven together, forming a four-dimensional fabric known as spacetime. Massive objects warp this fabric, creating gravitational fields that influence the motion of surrounding matter. Wormholes essentially act as shortcuts through this cosmic fabric, connecting distant points in spacetime and potentially enabling rapid traversal across vast cosmic distances. However, the stability and practicality of wormholes remain subjects of intense speculation and debate among theoretical physicists. While the existence of wormholes offers tantalizing possibilities for interstellar travel and time exploration, significant challenges and limitations temper these fantastical dreams. The intrinsic instability of wormholes, coupled with the formidable barriers posed by quantum forces and radiation, casts doubt on their feasibility as viable means of transportation. Moreover, Einstein's theory of general relativity imposes fundamental constraints on the speed of movement through spacetime, suggesting that even if stable wormholes existed, they might not facilitate faster-than-light travel, a cornerstone of many sci-fi narratives. Despite these challenges, the allure of wormholes endures as a beacon of scientific interest and exploration. The concept of the S-wormhole, named after its pioneering scholar, embodies the tantalizing promise of cosmic portals and alternate realities, inviting humanity to contemplate the mysteries of the universe and ponder the infinite possibilities that lie beyond. The quest for a unified theory that reconciles the seemingly disparate domains of gravity and quantum mechanics has spurred the search for a theory of everything, a comprehensive framework capable of incorporating all fundamental forces and particles in the universe. At the forefront of this endeavor stands the renowned theoretical physicist Michio Kaku, whose groundbreaking work has propelled the study of superstring theory. Superstring theory represents a dramatic departure from conventional ideal models, hypothesizing that fundamental particles are not point-like entities, but instead microscopic vibrating strings. These strings, akin to the strings of a musical instrument, resonate at specific frequencies, giving rise to the various particles and forces observed in nature. In this paradigm, the universe becomes akin to a grand symphony, with each particle corresponding to a unique harmonic resonance of these fundamental strings. One of the most striking implications of superstring theory lies in its potential to explain the enigmatic phenomena associated with dark openings, wormholes, and other exotic solutions to Einstein's equations of gravity. As strings traverse the fabric of spacetime, their dynamic motion leads to the formation of gravitational singularities and topological anomalies. However, the elegance of superstring theory masks its inherent complexity, as it necessitates the existence of additional dimensions beyond the familiar 3 spatial dimensions and 1 temporal dimension. These extra dimensions, hidden from direct observation, pose a significant challenge to human intuition. Nevertheless, applied models, such as the analogy of fish inhabiting a 2-dimensional lake, provide a glimpse into the elusive nature of these higher-dimensional realms. The compactification of these extra dimensions, akin to the folding of a rolled-up piece of paper, renders them imperceptible at everyday scales, yet their influence permeates the very fabric of reality. While the precise nature of these hidden dimensions remains elusive, their theoretical presence offers a promising explanation for the complex structures and anomalies observed in the universe. Furthermore, the mathematical underpinnings of superstring theory have sparked a renaissance in mathematical physics, revealing profound connections between dynamic mathematical patterns and physical phenomena. Indeed, the pursuit of a theory of everything has catalyzed the union of disciplines, shedding light on the deep interplay between mathematics and the natural sciences. Despite its theoretical elegance and scientific potential, superstring theory remains an untested framework, awaiting experimental validation. The elusive nature of extra dimensions presents a formidable barrier to experimental verification, relegating superstring theory to the realm of mathematical speculation. Nevertheless, the audacious vision of superstring theory continues to captivate the minds of researchers and enthusiasts alike, enticing humanity to embark on a journey of intellectual discovery and exploration. As we venture deeper into the known domains of theoretical physics, guided by the illuminating beacon of superstring theory, we confront the vast mysteries of the universe, poised on the threshold of a new era of understanding and enlightenment. The task of unraveling the secrets of quantum dark openings has long perplexed physicists, representing a monumental challenge to our understanding of the fundamental nature of the universe. Despite numerous efforts by physicists to tackle this riddle, the elusive solution has remained beyond our grasp, prompting Edward Witten of the Institute for Advanced Study at Princeton to describe superstring theory as the 21st century physics that accidentally fell into the 20th century. However, recent advancements have injected new hope into the quest for understanding quantum dark openings. Several groups of physicists have independently reported a significant breakthrough, revealing that string theory could offer a comprehensive solution to the problem, albeit within the more constrained context of 2 dimensions rather than the full 10-dimensional framework set forth by conventional superstring theory. While this represents a promising step forward, the quest for a complete resolution remains ongoing, with the complexities of the situations at hand presenting substantial obstacles. The search for a unified theory of everything beckons us to probe the deepest recesses of cosmic existence, where the boundaries between reality and theory blur, and the secrets of the universe await discovery. The study of dark openings carries profound implications for our understanding of the universe, challenging our notions of reality and raising questions about the nature of existence itself. The interplay between dark openings and other astronomical phenomena, such as neutron stars and gamma bursts, reveals the intricate processes at work in the cosmos. As researchers continue their quest to understand the nature of dark openings, they are increasingly focusing on the broader implications of these enigmatic objects. For example, dark openings are not isolated entities within the universe but are intricately connected to the life cycles of stars and the evolution of galaxies. Stellar mass black holes form when massive stars undergo supernova explosions, leaving behind dense remnants that collapse under their own gravity. This process contributes to the recycling of material in the universe, as black holes can feed on nearby gas and dust, enriching their surroundings with energy and radiation. Additionally, dark openings may play a central role in the formation of galaxies themselves. Many large galaxies, including our own Milky Way, contain supermassive black holes at their centers. These supermassive black holes, with masses millions or even billions of times that of the Sun, are thought to influence the dynamics of the entire galaxy. Their immense gravitational influence affects the motion of stars and gas in the galactic core and can even drive powerful jets of energy into intergalactic space. These jets, composed of highly energetic particles, may play a role in regulating the growth of galaxies by limiting the amount of material that can fall into the central black hole, a process known as feedback. The study of dark openings also has significant implications for our understanding of time and space. In the vicinity of a black hole, time slows down due to the intense gravitational field, a phenomenon predicted by Einstein's theory of general relativity. For an observer falling into a black hole, time would seem to stop at the event horizon, as all the information about their existence is lost to the black hole singularity. This raises questions about the fundamental nature of time itself and whether it can be reconciled with quantum mechanics. Understanding dark openings may also lead to new insights into the ultimate fate of the universe. Some theories suggest that black holes could be connected to the concept of cosmic inflation, where the rapid expansion of the universe in its early moments created the conditions for the formation of large-scale structures. As scientists continue to probe these celestial phenomena, the profound mysteries of dark openings promise to yield groundbreaking discoveries that could redefine our understanding of the cosmos.